Hi everyone and welcome back to my channel AA Economist. So from today onwards, we'll be starting off with a new playlist which is Advanced Econometrics, where we will start off with something called Multiple Linear Regression Model in the matrix version. In the matrix representation, we will see how to deal with Multiple Linear Regression Model. Now, if you are someone who haven't watched my previous playlist on econometric methods, I will give the link in the description. I would recommend you to see those videos first because there I have explained the classical linear regression model and multiple linear regression model in details. So I'll give the link in the description and also in the I tab button. So please watch those videos because that will give you clarity about what we are going to do today, right? So let's start with the matrix representation. The concept will be the same, only the representation version will be a little different, right? So let us see how we can handle that. So as usual, we'll start with the model setup. What will be the model? Our model here will be simply like this. Yi is the dependent variable. Here you have the first parameter beta 1 plus beta 2 x 2i plus beta 3 x 3i all the way up to beta k x ki plus ui for all I from 1 to up to n. So this is the model that we will work with. Now please understand this thing that what do you think? How many parameters are there in your model? What are the parameters in your model? This is the first parameter and this is the last parameter. So from 1 to k, you have altogether k number of parameters in your model, right? Can you see this? You have altogether k number of parameters in your model, beta 1, beta 2, beta 3, beta 4, all the way up to k, right? Total, you have k number of parameters. And how many explanatory variables are there? This is the first explanatory variable. This is the second explanatory variable. This is the kth explanatory variable. So altogether k minus 1 explanatory variable. So first x1i, there is no term as x1i. That is simply 1. So all the rest of the explanatory variables are there. So this many k minus 1 explanatory variables are there and k number of parameters are there. Where beta 1, this beta 1 is your intercept parameter and all the rest of the parameters are your slope parameters, right? This much I hope you know these things. I have discussed these things before also. So I'll not go into that more, right? So this is the model that we will work with. Now see, total, we have n number of observations. We have k parameters in your model and total n number of observations are there. Now, using this n number of observations, what you can do, you can form n equations, right? Using this particular model and using this n number of observations, what you can do, you can form n independent equations, n equations basically. So how will you write those equations? Let me show it to you. First equation will be when I equals to 1. When I equals to 1, this first value, what will be the model? What will be the model? It will be something like this. Y1, it will be instead of I put 1, it will be beta 1 plus beta 2. Then it will be x21, beta 3, and then you have x31. Then you have beta k, xk1 plus u1, right? I hope this much is clear. So in the model, wherever you see I have put the value 1. In the similar fashion, you can do this for 2. Y2, beta 1. So intercept stays the same. The rest of the portion changes. So it will be beta 2 and then you have x22 plus beta 3. Then you have x32 plus beta k. You have xk2 plus u2. Right? So you will do it for all the observations. The final observation will be when I equals to n. So it will be yn equals to beta 1, beta 2. Then what will this be? 2n, right? Instead of I, write n. So it will be 3n plus beta k xkn plus un, right? So what I have done is that using the observations, using the n number of observations that is there in your model, I have formed n number of equations. See, this is the first equation, this is the second equation, this is the nth equation, right? This is the nth equation, so all the way up to this. Now, if you have this kind of equations, n number of equations, systematic simultaneous system of equations, then what you can do, you can convert it into a matrix form. If you have these kind of a representation, you can convert it into a matrix form. How will you do that? So it will look something like this. Firstly, you will form a vector of all the outcome variables. So y1, y2, y3, all the way up to yn. See the left hand portion. So firstly you have y1, then you have y2, all the way up to yn, and all the rest of the values are here. So you take all these values and form a vector of it. Form a vector of it. This is the sign of a vector. You put it into a singular vector. Now, what you do something like this. Now see why I have done this. Here you have certain elements. So if you see on the right hand side of this equation, see the first column is everything is beta 1, right? In the first column, everything is beta 1. So what you will write, here you have beta 1. Now, if you want everything to be beta 1, what will be the first column here? What will be the first column in the first matrix? It will be all 1, 1, 1, 1, all the way up to 1. So you can multiply this beta with 1, that will be beta 1. This beta with this one, that will also be beta 1. And all the way up to this, all the values will be beta 1. So the first column is beta 1. And here you have the parameter beta 1. Now, second thing is this, beta 2. Now you want this to happen, beta 2 x to 1, beta 3, beta 3, beta 2. So we are only talking about beta 2. So wherever you have beta 2, see beta 2 x to 1, beta 2 x to 2, and beta 2 x to n. So how will you write this thing? In the matrix version, you will write simply this, x to 1, and then you have x to 2. See, match it from here, it will be like this, x 2, 3, and all the way up to x to n. This will be the second column, and here in the same fashion, you will do all the things. Total, you have k number of parameters, right? Altogether, you have k number of parameters, and here what will be the rest of the observations? x31 all the way up to xk1. So basically, I am writing the coefficients, nothing else, right? And this is x33, and in the same way, you have x3n. This is xk2. This is xk3, all the way up to xkn. Right, all the way up to xkn. And what will be the last vector? Last vector will be vector of the error terms. So this is u1, this will be u2, this is u3, and this is u, right? So this will be the entire matrix representation. So basically what I have done, I have separated these parameters and I have separated this coefficients of those parameters. So basically, see, this is the coefficients. These are all the coefficients and these are all the parameters. These are all the outcome variables and these are all the error terms, right? So what we can write from here is that this particular thing, you can write it as y curl. So this curl is a sign of the vector representation, right? This curl is a sign of the vector representation, which is known as the outcome vector. This is known as the outcome vector. Right, so this entire vector is the outcome vector. What is the dimension of it? Dimension means how many number of rows and columns are there. If you see, you have only one column, but how many rows? N number of rows. So the dimension is simply n cross 1. Number of rows times the number of columns. So you see, this is the first row, this is the second row, this is the third row, all the way up to n rows. So you have n rows, but only one column. That is why what we can say is that the dimension is n cross 1. Right, now next up, what you have, this particular matrix. This matrix, how will you write this matrix? In matrix notation, it is only represented as X. X is the matrix which is known as the design matrix. This matrix is known as the design matrix, right? So it is basically the matrix of all the explanatory variables. You can write in that fashion also. Design matrix means the matrix representing all the explanatory variables in your model. Right now, it is multiplied with something called the parameter vector. So this parameter vector is represented as beta curl. Again, it is a vector. See, this is also a vector. What is the dimension? You have k number of rows and one column. In the design matrix, what will be the dimension? You have C, n number of rows and k number of columns. So the dimension is n cross k. This is known as the parameter vector. This is called the parameter vector, which is beta curl. It is k cross 1, k number of rows, only one column. And finally, what you have plus this is known as the error vector. Error vector or the disturbance vector, right? Error vector or the disturbance vector. So this is how, and what is the dimension? The dimension is n plus 1. So basically what we can see from here is that so this particular model that we started off can be written in this particular form. Y curl equals to, you have x beta curl plus u curl. Right? This is what we have done. Y curl, that is the outcome vector, equals to design matrix into the parameter vector plus the error vector. That is what, this is the compact version of writing this, where this n has a dimension of n cross 1. This is n cross k, this is k cross 1, and this is n cross 1. These are the respective dimensions. Dimensions are very important whenever you are writing it in the matrix form, because later on when we will go into much complicated things, we will see that the dimension will come handy. So from the very beginning, I want you to know what is the dimension of which matrix and which vector, right? So if you multiply these two things, what will be the dimension? So this k has to match for multiplication. It will be simply n cross 1. See, n cross 1 plus you have again n cross 1. So n cross 1 plus n cross 1 will give you n cross 1, right? So that is how it works. So this is the entire, representation of this model. Now, as usual in CLRM, MLRM, we have studied some of the assumptions. Here also, we will look at some of the important assumptions of this particular representation, right? So the first assumption will be the known as the disturbance vector assumption. Disturbance vector assumption. The assumption is simple. This is the zero mean assumption. Disturbance vector assumption first is the zero mean assumption, which basically means that if you take the expected value of u curl, that is the expected value of the vector. Now everything will be in terms of vector and not in the individual terms. So we have written here the vector u curl, right? Vector u curl, everything will be, the expectation will be on the vector itself and not on the individual elements, right? So this can be written as zero curl. The assumption is, disturbance variance assumption is expected value of this error vector will be zero vector, right? Zero is also a vector. So how will you write it? It is simple. Expectation of u curl can be written as expected value of u1, u2, u3 all the way up to un. See, this is the u curl vector which we have written here. u1, u2, un. This is n cross 1 vector. That is what I have written. Expected value of u1, u2 all the way up to un. Now, by the properties of expectation, you can go about this. Expectation of u1, expectation of u2, expectation of u3 all the way up to expectation of un. Now, from the CLRM and from the MLRM assumptions, we know the individual error terms, expected value of the individual error terms 0, right? Expectations of the individual error terms are 0. So this is 0, 0, 0 all the way up to this 0. So this will form a 0 vector. So this can be written as a 0 vector, again 0 curl. So simply expectation of u curl will be equals to 0 curl, and this is the first assumption of your model, right? I hope this much is clear. So this is the assumption on the error vector, not on the error terms, but on the error vector, right? Now, from this, what you can say, from this, you can say the linearity and the non-stochastic assumption that x, we know x is non-stochastic. X is basically non-stochastic. This we have done in CLRM as well. Non-stochastic means it does not have any probability distribution. Now, if this is the case, what will be the value of expectation of y curl? Remember that y curl is what? Y curl is expect x into beta curl plus u curl. This was the representation. Now you want to find out what will be the expected value of this y curl. So what will this be? Let me write entirely. So x beta curl plus u curl. So you can separate them out, x beta curl plus expectation of u curl. Now expectation of u curl, we have just shown you that this is zero curl. So what will be expectation of x beta curl? It will be simply x beta curl plus zero curl. It doesn't matter. So it will be coming out to be x beta curl. Now, how can you write this? You can write this only because x is non-stochastic. Whenever something is non-stochastic, if you take expectation on it, only that value will be returned. So x is non-stochastic means it will take fixed values in repeated sampling. That is why it does not have any probability distribution. That is why if you take expectation on some scalar quantity or matrix also, so here see every value in this matrix has a specific value, fixed value. So if you take expectation on each of these elements, they will only return you some fixed elements only. Those fixed returns, fixed elements only. That is why the expected value of x will be simply equals to x. Right? Expected value of x is simply x, and beta curl, this we will prove that that the blue property again holds. That is unbiasedness property also again holds. That is why expectation of beta curl, if you take expectation of beta curl, that will be simply equals to beta curl. So, or the population parameter beta. Expected value of this will be equals to beta curl. That is why you can write this thing. So, linearity basically holds. Linearity basically holds, right? And this will be the second assumption that x is non-stochastic, and from that property only you can derive that expected value of y curl will simply be equals to x into beta curl, right? This is the second thing. Now the third property is in terms of homoscedasticity. This also we have taken separate classes beforehand. So I'll not explain the concept, but I will show you how to represent it into matrix notations, right? So homoscedastic error term. Homoscedastic error term in matrix representation can be denoted as something called the var-povar matrix, right? We will form something called the var-povar matrix. Var-povar matrix. What does it look like? It looks like this. Expectation of y curl minus x beta, y curl minus x beta, and a transpose of it. This prime means the transpose of it. What does this mean? This basically means expectation of, what is this? Y curl minus x beta curl. Can you say what is this? See, y curl minus x beta curl, if you take this on the left hand side, it will be only u curl. So it is simply u curl into u curl transpose, right? Var-povar matrix is given by this, which is expectation of u curl transpose. Now what we do? We will write it into the form that we have. So u1, u2, all the way up to un, and into, if you take the transpose, the row becomes the column becomes the row. That is the transpose basically. u1, u2, un. Now again, if you want to multiply, the dimension will play a crucial role. See, this is n cross 1 and this is 1 cross 1 cross n. So if you product it, take the multiply, then what will be the dimension? It will be n cross n, right? It will be n cross n. So for multiplication, this dimension has to be the same, and the ultimate matrix will be of this dimension n cross n, right? So if you do the multiplication, what will you get? Let me write it down. Expectation of n cross, there will be an n cross n matrix. What is the first element? u1 square. First will be u1 square, and then what you will see? u1, u2. This will be u1, u2 all the way up to u1, un, right? u1, un, then you have u2, u1, then you have u2 square, all the way up to U2, UN. And in the similar way, here you will have UN, U1, then you have UN, U2, all the way up to UN square. And the expectation of it. So this now becomes an n cross n matrix. Now, if you take expectation, expectation can be on all the elements of this matrix. Individually, you will take expectation on all these elements of this matrix. If you do that, can you tell me what will be the expectation of this first element? What do you think? You can basically pause the video and think. This we have done also earlier. If you remember, according to the homoscedasticity assumption, this has to be exactly equals to sigma square. This is a constant. Error variance, so basically, the error variance is a constant. It does not depend on the value of i's, right? So this will be sigma square. And what about this? Ui, uj. What will be this? This will be simply 0 due to the non-autocorrelation assumption. So the homoscedasticity assumption plus the non-autocorrelation assumption, both can be depicted using the var covariance matrix, right? Var covar matrix. Now see, expectation of u1 square, this will be simply sigma square. Now expectation of u1, u2, this will be simply 0. All the way up to this, all the terms will be 0. This term will also be 0. Now expectation of u2 square will be what? This is sigma square. Now again, all the way up to this, all will be 0. Again, here it is 0, here it is 0, or only the last term, this will come out to be sigma square. And it is again an n cross n matrix. And this matrix is known as the var covar matrix. Why this is so? See, here all the diagonal terms will give you sigma square. All the diagonal terms will give you the homoscedastic variance, right? Can you see this? All the diagonal terms, this term, this term, this term, all the diagonal terms will give you homoscedastic variance, and on all the off diagonal terms will give you the non-autocorrelation assumption. Non-autocorrelation means that all the the two error terms, when I not equals to j, the two error terms will be obviously 0. The expected value of them will be 0. They are uncorrelated with each other. So that is why all the rest of the terms are 0. So if you take sigma square common, you will get an identity matrix 0, 1, 0, 0, 0, all the way up to 1. So this can be written as sigma square, and this identity matrix, we write it in this fashion, IN. IN represents the identity matrix of dimension n. Right? So this is the final form of the var covar matrix. This is also another assumption. So this is the third assumption of basically the MLRM model in matrix notation, that homoscedastic error variance and the non-autocorrelation, all the assumptions will hold, and those can be represented. Those can be formally, represented using the var covar matrix. So here the diagonal terms show you the variance, and all the off diagonal terms shows you the covariance. That is why it is called the var covar matrix. Var covar matrix, variance is the diagonal terms. See, all the diagonal terms have the constant variance. That is homoscedasticity, is constant variance. Error variance is constant. This assumption. That is why it is the variance matrix, and covariance because all the off diagonal terms, they are 0. And this represents all the covariance terms. Covariance of ui, uj basically. That is why expectation of ui, uj, all the rest of the expectations are 0. Expectation ui is 0, expectation uj is 0. That is why it is the covariance also. That is why it is the var covar matrix. And in MLRM, in the simplest form, it will be simply sigma square into the identity matrix of order n. And this will be the third assumption, right? I hope this much is clear. And there is another assumption, the fourth assumption, which is called the full rank assumption. Now the assumption will be on the design matrix, full rank assumption of X. Now, since we are talking about the matrix, the rank plays a very crucial role, right? Rank plays a very crucial role. Previously, we have said that X is a non-stochastic matrix. That is what we know, but it also has to be full rank. What do we mean by full rank? That can be written as this: rank of X, rank of this design matrix X has to be exactly equals to K, and which has to be exactly less than N. Now, do you remember what is K and what is N? K is the number of parameters which is used in our model, right? This we have discussed previously. K is the total number, beta 1, beta 2 up to beta t. That is the K. K is the total number of parameters and N is the total observations. I is varying from 1 to N. So this basically means the total number of parameters. This basically means the number of parameters of our model has to be strictly less than the number of observations. This was one of the assumptions we have discussed in our CLRM. Now, see why this assumption is very important. This assumption is basically very crucial. It's one of the most important assumptions, which is specific to the nature of the MLRM model, which basically means that the determinant of x prime x will be not equals to 0. X is non-singular matrix. Basically, this assumption will ensure that. Why this is so? Do you remember what is the definition of rank of a matrix? Rank of a matrix basically means that the number of linearly independent rows or columns of a matrix is called the rank. Right, this is the rank of a matrix. So for example, if I have to explain to you, suppose I take a very small example. Suppose I take this matrix 1, 2, 2, 4. Now, can you tell me this dimension is 2 cross 2? Can you tell me what is the rank of this matrix? Suppose I call it A. Can you say what is the rank of this matrix? If you see in this matrix, the second row of this matrix is simply 2 times row 1, right? See, this is 2, 4. This is the second row and this is the first row. So if you multiply each of the elements of the first row by 2, you will get the second row, right? So R2 and R1 is completely dependent on each other. So how many independent rows and columns are there in the matrix? How many independent rows are there in your matrix? The answer is only one. There is only one independent row. Also see, here also if you multiply this, you will get this term. So columns are also dependent with each other. So there is only one independent row and only one independent column in your matrix. That is why the rank of this matrix A will be strictly equals to 1, which is less than the number of rows and number of columns. That is, it is not full rank. In that situation, if there is any kind of dependency between the rows and columns of your matrix, then you cannot have a full rank, right? That is the concept. Full rank, for full rank, if a matrix is of full rank, then all the rows and all the columns of the matrix will have to be linearly independent of nature, right? That is what I have written here. Number of linearly independent rows and columns of your matrix is called the rank. So if I say that the design matrix has to be of the full rank, it means the rows and the columns of this design matrix has to be linearly independent of each other. So there is no sort of dependency. You cannot express one row or one column of this design matrix in terms of the other rows or in terms of the other columns. Now, why this is important? Can you pause the video and think for yourself? Why do we need this sort of independence assumption? The answer is very simple, because we want to avoid multicollinearity in our model. So if you remember what is multicollinearity, multicollinearity appears if there is any sort of linear relationship or high correlation between the explanatory variables of your model. Now, if dependency comes, then this correlation also comes, right? If there is any sort of linear association, any sort of dependency, then the problem of multicollinearity will arise in your multiple linear regression model. And if multicollinearity is present, then you cannot estimate the parameters separately in your model, right? I have made separate videos on multicollinearity. If you haven't watched those videos, I'll give the link in the playlist. Please check that out. There I have explained in details what will be the consequence of multicollinearity and why it is bad for our model, right? So basically what we can say, we can write like this, that suppose rank is equals to, say, k minus 1. Suppose it is strictly less than k. Here I have said that k, it has to be exactly equals to k. So we'll prove why this is not so. Why rank cannot be k minus 1. If there is k minus 1, it means it is not full rank. It is not a full rank matrix, which basically means one variable, at least one variable, is dependent on others, right? Similarly, if you write k minus 2, then there will be here you will have two variables that will be dependent on the others, right? In the similar fashion, it will continue whenever you take k less than 1. So x will have the problem of multicollinearity. Multicollinearity. That is why you cannot estimate the parameters separately. You cannot estimate the model separately. This basically means rank cannot be equals to k minus 1, which basically means rank exactly has to be equals to k, right? This is how you can give the logical reasoning to prove this statement. Also, another aspect is that you can ask me why I have written this k is less than n. So why we need parameters, number of parameters less than the number of observation in case of rank. So if you know one of the properties of rank of any matrix has to be less than equals to minimum of the number of rows or the number of columns, right? This is one of the important properties of rank. Rank of any matrix has to be less than equals to minimum of row and column. So from this property also, you can see less than equals to minimum of how many number of rows are there. You have n number of rows, and how many columns are there? K number of columns. And which one of them is lesser? Which is minimum? N is minimum or K is minimum? So the lesser value is k. Obviously, so from this expression also, you know the rank has to be less than equals to k. Now we have just proved that rank cannot be less than k, right? We have just proved by the reasoning I have given you here, because problem of multicollinearity will arise. So this less than version is not allowed. That is why rank of x has to be exactly equals to k. From this reasoning also, you can say this thing. Now, why we need that the number of parameters has to be less than the number of observations? Because it is the case that in normal equation, I have told this before, that in case of normal equation, you at least need the total number of normal equation has to be exactly equals to the total number of parameters that you want to estimate in your model. And in order to do so, you need sufficiently large number of observations. If you have to estimate the k number of parameters in your model, you at least need k number of normal equations, and those normal equations can only be formed in a valid format if you have a large sample, if you are taking enough or sufficient number of observations in your model. The higher the number, the better it is. So n goes to infinity. As you tend your n is going towards infinity, the better will be the model prediction, because your sample will go towards the population, and as and when you can represent the entire population, your predictions and your estimations will be better, right? So that is why it is always advisable that you start with sufficient number of observations in your model, be it classical linear regression model, be it multiple linear regression model. You always need sufficiently large number of observations, and that it is advisable that that is strictly larger than the total number of parameters that you estimate in your model. So this assumption also leads you to the no multicollinearity, right? No multicollinearity should be present in your model. This basically means that if rank of x is equals to k, exactly equals to k, this ensures that no multicollinearity should be present in your model, which basically means that not all the rows or columns are linearly dependent in our model, right? So this is all from my side today. So what we have done today is that, let me give you a quick recap. So our agenda was to, set up the model and also to explain the assumptions that we need for our multiple linear regression model in matrix notation. So firstly, we have seen how we can convert this original model into n different equations. Depending on the number of observations, you can form n different equations. This is like this. Now from those equations, you can convert it into this matrix and in the vector form. So you have three vectors here: outcome vector, parameter vector, error vector, and here you have the design matrix. This is the design matrix. Design means it is the matrix of all the explanatory variables that are present, and we have seen how to find out the dimensions for each of these matrix, which I said that it is very important to know the dimensions. It will come handy later on. Now, what are the assumptions? The first assumption is on the error vector. Since we are dealing with matrix and vectors, everything that we will talk about, that will be in terms of vectors and in terms of matrix. That is why expectation will be not on the individual error terms, it will be on the entire vector. That is why you call, that is why this call comes into place. Now this is how you do this. So expected value of this error vector will be zero vector. This is basically zero. This is not individual zero value. All the elements are zero, and that is forming a vector in itself. That is why it is zero call. Zero vector is that there. Now the second assumption is that x has to be non-stochastic. That leads you to the linearity assumption as well. That expected value of y curl will be simply equals to x beta curl, because the expected value of the error vector is basically zero vector. That is why we can ignore it. Now the third assumption is homoscedasticity and non-autocorrelation. That can be non-autocorrelation. This will be non-autocorrelation. That can be represented, both can be jointly represented using the Var-Covan matrix, which is basically special to this representation only. We haven't talked about Var-Covan matrix previously. This is something unique to this discussion. So in case of Var-Covan matrix, we start with this kind of a representation: U curl transpose. So remember, whenever you have transpose on the right hand side, you will get a matrix, n cross n matrix. But if you put transpose here in the middle, you will get a constant value. That we will see when we will go into estimation in the next class. We will go into the parameter estimation in the next class. Then we'll see how to do that. So now, as of now, you will form this vector. So this matrix, basically matrix, and that will help you to find out what is the Var-Covan matrix. That can be represented as simply this: sigma square into the identity matrix of dimension n. That will be the vector Var covariance matrix, which basically assume both the assumptions, homoscedasticity assumption and the non-autocorrelation assumption. And the fourth and the final assumption is the full rank assumption of matrix X. This is also unique to this discussion, that rank of X has to be exactly equals to the total number of parameters of this model, which is strictly less than the total number of observations that we are using, because rank represents the total number of linearly independent rows and columns. And to avoid the problem of multicollinearity, we always need that the rows and the columns of the design matrix X are independent or linearly independent of each other, so that we can estimate all the parameters separately in our model, and we can form sufficiently large normal equations in our model, right? So that is the explanation, and I hope you like this video. If you do, then please hit the like button and do subscribe to this channel, A in Economist. And I'll be making a detailed playlist on advanced econometrics now, and we'll see in the next video. We'll be going into the parameter estimation. We'll see how in the matrix version of this model we can estimate the parameters, and we'll find out the blue properties as well. Right. So thank you so much for your time, and stay tuned for the next video.